Alright, just showing off some of the fractal point placement stuff that I've been working on. Here I've got, this is the biggest one I've done. I started with that because, well, here, this is why. It took 530 seconds in order to run the CPU side generation of the points beforehand, because it's like 27 nested for loops or something crazy like that. Anyway, so this shows off how it's being done. Let me zoom out some, and you can see the whole. Okay, what's being shown here is a 3 by 3 by 3 voxel block, right? And each one has been divided into 27, and then divided into 27, and then divided into 27, and then a point has been placed at that particular point. So this is 3 by 3 by 3 with 500 million or 500,000. I can look at the exact figure, but it's 531,441 points per voxel. So it's got kind of a cool fractal structure to it. Those placements are based upon, the first one's based upon the spacer, right, from the center to the here, or, well, actually, no, it's from here to the edge ones, and then it uses the spacer squared, and then it uses the spacer cubed, and then the spacer to the fourth. So by giving it a higher value of the spacer value, you can make that a tighter grouping. Because let me show you how the spacer value is actually used. Yeah, so the these for loops just range from -1 to 1, and then when they're at -1, they're using a negative amount times the spacer. When they're at 0, they're using a 0 times the spacer, and then at 1, obviously 1 times the spacer. Alright, and so there's one for these first order spacers, then the second order, and third order. Yeah, there's even fourth order here. That's the 500,000. And I've got it so it prints some sort of representative quantity of those loops. It makes kind of a cool pattern, actually, if you look. Also, if you're watching it while it's running, it's kind of a cool thing to watch. But, yeah. So, I can show you some of the other numbers of points that you can use. Go ahead and quit this. Alright. I'll show you, for example, 27 points per voxel. Runs a hell of a lot faster. Now, you can still see basically what's going on. Same kind of scheme. Only it's just subdividing one time rather than the 4 times, I guess, for the other one. Subdividing into 27. And of course, there's still the single point per voxel. Which allows you to just use one. So, I'm actually going to put this back to 0.5 because it's not fully covering the color space when it's doing that, because it's hard coded in the well, the color value it gets. It's not hard coded in the shader, but that functionality is. If I wanted to change it, I could set up some uniform variables in order to handle that are used in the fragment shader to signify the min and max extent for each one. My next thing I'm gonna do is make a class-based interface for this to try and expand it a little bit more. Here's 189 points per voxel. It places 7 at each of the 27. It's kind of a cool one. I like it. It started me on the fractal thing. Or that might have been the second one I did. Yeah, actually, yeah. Because it did the 36 where I wrote out all the spacings. I wrote all this out. Well, I copied it and then filled in the spacer things, but until I figured out that it was a lot simpler to do it this way, and because it's essentially doing the same thing, it's just a little bit different way to handle it. That's a lot simpler. In terms of the amount of code, it's actually it takes forever to actually run through it, because it's once you get down here, it's 500,000. This will run 500,000 times for every voxel, right? Which is a lot, and like I showed you before, it was 530 seconds in order to actually run through that for a 3x3x3 voxel cube. So that's kind of what's going on there.